Greetings to all, welcome back to the channel. So in this video we will be learning about the parallel resonance circuit. So what is a parallel resonance circuit? For that I've shown here a diagram where we can see the parallel resonance circuit. This is a source which is AC in nature with some frequency. So for this we can write that V max into sine some omega t. This is the source, and this is a resistance, this is inductance, and this is a capacitor. So what is the condition for parallel resonance circuit? So for that we will be finding out first the resistance, first the total impedance of the circuit, or total admittance is better. What is admittance? Admittance is 1 upon impedance. Okay, so what is the total admittance of the circuit? Y is 1 upon R plus 1 upon omega L with a J and plus J omega C. So this is the total admittance of the circuit. So what will happen? Actually what happens is, when this total admittance is minimum, and when this total admittance will be minimum, when these two quantities will cancel out each other. This is a basic condition for resonance circuit. So for in case of the series also and in case of parallel also, what happens that the inductor and the capacitor share voltage in case of series, and here they are sharing the current in case of the parallel resonance. So what will happen? This current, this is the current, it will be totally flowing through the resistance in case of the resonance, and inductor and capacitor will be exchanging current with each other like shown here. There will be a circulating current. So at this point the current will be 0, and this condition is given by a special case where omega is equal to 1 upon under root LC. So whenever our omega or frequency, where omega is 2 pi into frequency. So whenever the frequency or the frequency in radian per second is equal to 1 upon LC, where L is the inductor and C is the capacitor, at that moment what will happen? The inductor and capacitor will be exchanging the current, or there will be a circulating current between inductor and capacitor, and the overall circuit will be behaving as a resistive circuit. This overall circuit will behave as if it is only containing a resistance with R. So this is a basic idea behind the parallel resonance circuit. What we'll be showing you in this video is a simulation using MATLAB. So here I have shown a voltage source with a voltmeter which is measuring the voltage. Here I am also measuring the current for LC region for each of the component, for resistor, for inductor, and for the capacitor also. So this is the overall circuit, and now we will be simulating it. So what we have learned is the total circuit behaves as if it is a resistive circuit, and this current which is going towards LC should be 0. So net LC current should be 0 in case of during the resonance. Okay, so now I'll be doing this. So let's go to the MATLAB directly. So now you can see the MATLAB window. So in this I have made the similar MATLAB program. So here is the voltage source. What is voltage source? You can see here it is a 10 square root 2, or the peak, the RMS current of this voltage is 10. Okay, square root 2 means I am giving the maximum input. The frequency 50 Hz. So let's put right now 40 Hz, and let's see what will happen. At 40 Hz the resistance I have taken 1 ohm, inductance 1 millihenry, and capacitance 0.1 millifarad. Okay, so now I am running it for the 10 seconds, and let me see what are the responses. Now you are seeing that the current started with a very high RMS value, and now it is returning to the its steady state. So this condition is known as transient condition, and later the current will settle down around 2 or 3 seconds. So here what you can see, I am showing you 3 currents at any given moment. So on the right hand side you can see that this blue color shows inductor current, the yellow color is showing the capacitor current, and red one is showing the our resistance current. So what you can see here is that the inductor is drawing high amount of current, and capacitor is also drawing current, and all three are drawing current. And because of these three, you can see that there is a net phase difference at any given moment. we can see the phase difference here also. Here the on the left hand side here, the red one is showing the I total current and blue one is showing the V out. So this is the voltage and the current is lagging behind because the inductor is drawing more current. So at this moment the circuit is behaving as if it is a inductive circuit because voltage is here and the current is lagging behind. This you can see at any given moment. Now what we will be doing is we will be seeing the net LC current, the current going to the this LC circuit. So here we can see here you can see that blue one is the inductor current, yellow is showing the capacitor current, and this red one is the net current drawn by the LC section. So this red is right now it is not zero. Okay, so at that moment where these two or the inductor or capacitor current will be equal and they will be cancelling out each other, at that moment this red or the net inductor current will become zero. So now we will be, I have already calculated the frequency which is 50 Hertz resonant frequency. So now let us see at resonant frequency. You can see, so this is the transient response, the initial response which is the circuit is giving. Now the circuit is going towards a steady state. So we will be seeing around 6-7 seconds where the current will be settling down and will be stable. For that purpose we can see net current right now. So here you can see that this red line is showing that current is going towards zero. So when this current will settle around 5 or 6 seconds, you will see that this red line which is showing the net LC current or the net current the LC section is drawing will become exactly zero. So let's zoom in this section. So it is still going towards zero and you will see that the net L current or net current that drawn by LC is zero because inductor and capacitor current are net cancelling each other. Here you can see blue is the inductor current and yellow is the what current, our capacitor. Similarly we will be seeing here. So here you can see at this moment the circuit will be exactly the resistive circuit. So here you will not be able to distinguish between here you can see that the circuit is behaving as if it is a pure resistive circuit because there is no phase difference between red color is showing the current and blue is also going with it. You can see slightly that blue is also shading this region. So there is no phase difference between the current and the voltage. So the circuit is behaving as if it is a pure capacitive, pure resistive circuit. So now we can see here also you can see the resistive current as red on the right hand side and the inductor current and the capacitor current are exactly cancelling out each other. So what will happen if we increase the frequency further? So if we increase the frequency further to 60 Hertz, what will happen? The circuit will behave as if it is a capacitive circuit. And what is a sign that tells us that the circuit is capacitive is that the current will lead the voltage. So at any given moment or at a given time we will see that the circuit will be behaving as the capacitive circuit. So here you can already see that this yellow color is having a higher magnitude and yellow color represent here the capacitor current, I capacitor. You can see here. Now here you can see the red one is showing the current on the left hand side and it is leading the voltage which is blue one, and here also the capacitive current is being very high compared to the blue one which is the inductive current. So you can see the peaks and from there you can measure the RMS of the current. So this is all about the resonance circuit. So earlier we have simulated the series resonance circuit and this is a parallel resonance circuit. So what is happening here is you can say what is happening here is we are having so during when this is a frequency and this is a resistive this is, so as the frequency is increasing the circuit is going from like this. So this is the admittance. Okay, this is admittance. So admittance is decreasing or we can say the impedance is increasing because impedance is this is Z. So okay, this will be equal to R and this is Y. Y will be equal to 1 by R. and here the circuit is inductive, and here the circuit is capacitive, and at this particular moment the circuit is resistive. Okay. So this is a kind of a special circuit which is a parallel resonance circuit. So this is all for this video. Thank you.